Hey, good morning, students. And today we'll be working on algorithm called AdaBoost. And this is some algorithm that is will be a prerequisite to understand another algorithm that is very famous, and that is a gradient boosting, and then also XGBoost, right? In which the whole industry is using. So yeah, so let's study what is AdaBoost. So the idea is a very nice. The intuition is that we can combine several weak learners. We can create a very powerful ensemble learner, right? So, for example, the first classifier, right? Let's call it D1. It classifies this, right? But we have a lot of errors, right? That is the here. Okay, here, this 3 plus is not correctly classified because it's supposed to be on this side. We increase the weight of this, hence D2 would try to prioritize these three samples. But at the same time, but because of you doing this D2, you create a three incorrectly classified sample. Once again, you increase the sample, increase the weight of the sample, and now you get another classifier. And finally, once you combine these three weak learners, you'll get a very good classifiers that can kind of solve this entire problem, right? So that is the whole idea of AdaBoost. But what I want everyone here to understand is the philosophy, right? The intuition that when you combine several weak learners, you can get a very powerful learner, right? And this weak learner is actually very, very easy to train. The only thing we need to know is how to update this weight, right? Which should not be that difficult, right? Okay, so now let's look at the AWS. The hypothesis function is nothing but alpha 1 with yeah, h1x plus alpha 2 h2xi, etc. Right? So this h1 is the first classifier, h2 is the second classifier, and is the last classifier, right? So h1 could be this, h2 could be that, and h3 we could be that, right? And alpha 1 is some number that we basically saying that, hey, how much we trust D1, D2, and D3, right? So H1 is for D1, H2 is for D2, and alpha 1 is for how much we trust D1, and alpha 2 is how much we trust D2, for example, right? The higher number, it means we trust it, right? Zero means that we don't give any significance. And negative means that it's so bad that we should flip the predictions, right? So those are the numbers that you can get in alpha, right? And each of the alpha will not be the same. So it's not like the learning rate. All right. And finally, if we want to get the prediction of that sample I, it's simply getting all the S classifier, well classifier, sum of, and then you take the sign, right? And that would give you box number 4 right over. So how do we define what is a good classifier? First of all, we need to define how do we calculate the errors. The errors is nothing but whenever that sample is not equal to that actual y token, then we have this indicator, right, to turn on and off. So this will give us a 0 and 1, and this will be the weight, right? So based on that, we will have the weighted errors as epsilon s, right? Now, of course, this number is in the range of 0 and 1, right? So because so for each of the classifier, we will have this epsilon s, right? So you can imagine this could be epsilon 1 that show us how many errors we have for that classifier 1. In the beginning, we can initialize the weight as 1 over m, which makes a lot of sense. And the total for example, the number of when you add all the weight of all the samples is one, right? So 1/m, and then when you add everything, it's one, right? So let us see how this look like in action, right? For example, let us write some code here. So let's say I have y hat equal to np array, sorry, -1, 1, -1, and 1 and 1, right? So let's say that is the predicted one, right? And the real y is 1, 1. So sorry. Okay, no way. 1, 1, 1, right? And this part is nothing but just simply, we can simply say y hat dot sum, right? And of course, np, so we can clear off the restart run all. All right, and give me just 1 second. All right, so this should be that. All right, so now we got 2, right? That is, there are 2 numbers that are incorrectly classified. So that would be right here, right? That is how many we're incorrectly classifying, right? And the weighted errors is extremely simple. That is, we can say that m is equal to 5 because we have 5 samples, and w is np dot foo m 1/m, right? So we have so right here, if we print the w, we will have w1, w2, everything is basically equally distributed. That is 1/m. And then we can calculate the E is nothing but the weight of which y hat is not equal to y, right? Dot sum divided by the sum of w, and now you got E. All right. So it seems like very complicated, but no, it's not, right? And that would explain this, right? So if your classifier give you these results, the error of your classifier is nothing but 0.5, 0.4, right? Great. Of course, you can try to play around with this number and see how the E change. All right, great. Okay. The next thing we can see is how do we update the weight, right? So remember, if how do we update the weight of each sample, right? Well, the idea is that if the predictions is in the same, for example, if we predict 1 and this is 1, then this is positive, right? We want to flip the sign so that the weight won't be updated as much, right? But at the same time, if this is -1 and this is 1 or vice versa, then we want this one to, we want some alpha to the weight so that W is 10, right? So that is something we want to do, hence this formula, right? Even though this formula looks very scary, it's not at all. It's just some mathematical manipulations, right? And of course, once we get all the weight of all the samples, we have to normalize by adding all the weight to make sure that they always add up to 1, right? And here, alpha is nothing but 1 minus epsilon divided by epsilon, and you just simply apply log, right? Here is just log E, so for convenience, we call it ln, and 1/2 is could be any numbers actually. It doesn't really matter here. And the range of alpha is minus infinity to infinity. Again, alpha is a reciprocal of error. So if the error is very high, we want to make this very low because we don't want to trust this classifier. When the error is very high, then the alpha is very low. If the alpha error is very low, the alpha is very high, right? That means we trust this classifier a lot, and this will reflect in the hypothesis function later on. When we take each of the classifier, multiply with the alpha, it tells us how much we should trust that classifier. All right. So we can actually plot the relationship between alpha and errors to make sure that it's clear. So I have prepared some code. Right. So I assume that E is some number between 0 and 0.99, and I got 1,000 numbers. And here, this is just for making sure I don't get division by 0. And then the alpha is nothing but that. And then I plot this graph, and you can see that the the bigger the error, the lower the alpha, right? The smaller the error, the higher alpha, right? That is the more you trust that, right? So that is how this function comes from. It's basically try to come up with a function that behaves like this, right? All right, so now we update this, right, using this, and so we can slowly try to run one by one and try to understand how this function looks like, right? So starting from here, so we're gonna do this two things first here. So let's say we have, if I'm not wrong, we already have this, right? And the next thing we can do is, of course, we can now calculate the, if you recall, this is the E we have. All right. Anyway, let us do the E again. I'm not sure this is the E we want. So W equal to NP dot foo, M comma 1 over M, right? And so that is the W we have. And we can say E equal to W Y hat dot sum W and E, right? So that is 0.4. So now we can actually calculate alpha J, right? So alpha J is 1/2 ln 1 minus blah, 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 right? So I have already prepared this. So that is nothing but this one. We can get that the alpha is 0.2. That means because the error is quite high, so the alpha is 0.2. And we can look at this graph whether it's true, right? So if the error is 0.2, alpha is around sorry, the error is 0.4, right? Yeah, the error is 0.4. So when the error is 0.4, the alpha is around 0.2, right? So you can see that it behaves exactly that. Now we can now try to do this pair first. So we can do y hat multiply y, right? And we'll get this, right? So what is this? This means that the sample, these samples are correctly classified, and this one is not correctly classified, right? So hence, you can see why this operation is so useful, because when they are different signs, it works that way. You may have one question like, what if it's like -2, or if there are more classes? No, AdaBoost is made for binary classes only. So that is only -1 and 1, right? So that's why this formula works, right? But don't worry too much. We won't use AdaBoost later on, but it's essential that you learn this algorithm, how it works, before we move on to more powerful algorithm like gradient boosting. All right, so that is one hand. Now we can actually multiply this one and see how it looks, right? So we already have alpha j, right, which is that. So we can do minus alpha j multiply with y hat, multiply with y, and to make sure things are nice, we multiply with that, and we can get this, right? So you can see that this given, right? So whenever you're correctly classified, right, they will be minus. right? And when you incorrectly classify, it will be positive, right? So you flip a little bit, right? And please note, observe this behavior and see why is that, right? So the next thing we want to do is, of course, take the E, right? So to take the E is nothing but simply this, right? Right, and we do that, and we can see that, oh, it's nothing. Taking an E is nothing. The magnitude is still relatively the same. That is, this one is bigger than this one. This one is still bigger than this one, right? So why do we want to take the E? Well, the E just make sure everything is positive, right? So it's useful for making sure things are stable, and also at the same time, if we want to make it probabilistic, then it's very nice, right? Great. So now we can actually calculate the new W based on this E part, right? Which we already calculate. So let's try this. So W equal to W multiply with this one. Right. So let us print the previous W, right? And let us print Y hat and Y to make sure we know. So we observe that the first and the third samples are incorrectly classified, and now we print the new W, and you can see that the first and the third samples get bigger, right, based on this equation, which is splendid, right? And of course, you can notice that we need to normalize this, and then this normalization is nothing but just simply W equal to W divided by sum of W. And by doing that, it's just a simple trick to make sure everything is nicely added to one, right? Great. So hopefully, I think you understand the intuition of this algorithm is fairly easy, and it works, right? So you just keep looping this many times, and eventually things will be okay, right? According to the number of classifiers you want, right? Great. So let us try to work out this from scratch, right? So firstly, I'm gonna run this iris sample again. Okay, this is not an iris sample, right? This is a make classification. So I got this, and I have defined some parameters right here. So M, and I want 20 classifier. Each of them is just a tree, right? And it's a very small tree with only 2 nodes, right? And by making sure that it's only a tree of one depth, it's basically one line. It's basically resemble this one, right? It's a line, right? Because it only decide like one question, right? So this simulate that, right? And this is nice, right? You can see that by using very weak learner, but combining 20 of them, it really works well, right? So I create that many of the decision trees classifier. And then of course I initialize W and alpha. So in the beginning, alpha, I just have S of them, but I will set everything to zeros, right? And then I just loop each of the weight, each of the model, and I'm gonna train them, right? And it's very neat. It's very nice that this decision tree created by sklearn already allow me to just simply provide the sample weight, right? How much we should trust it, and finally I predict the errors, and then I can calculate the E, how much errors that this classifier create, and then I can calculate the alpha for that particular classifier and put them into a list, put them inside J, so that we know which one is which. And of course, we can print it later on. And now we can actually create a W, right? And you can see that this W will be used later on again in the next model, right? So the next model will have W differently, right? And it will prioritize on different W, right? So then, but every classifier will have the alpha, right? Which is independent from every model itself, right? So that is great. And yep, so you can see that we have 20 classifier and each of them has different alpha, right? And you can see that, well, the first classifier seems to be very well trusted. And then they are, these are all the, how much we can trust each classifier, right? Now, based on that, we can now make predictions, right? So we can do that. And then we can take the first model, predict it, right? And then we simply add all of them together, and this will give us the hypothesis function, right? Keep adding all of them. And then finally, the final prediction is nothing but taking the sign of them, right? And you can print the classification report of that, and hopefully, oh, so that's not bad, right? So it's a 0.97 and it works great, right? So hopefully you enjoy AdaBoost, and I think it's a really powerful idea, and it still stands true until even today. That is, when you combine several weak learners, it actually can create a very powerful algorithm, right? It's like in the real world when you combine many people who really work hard, but they may not be the smartest, but when they work together, it will create amazing jobs, right? Thank you very much, and see you in the next tutorial.